Yes, presenter mode. Fine, you can start now.
Okay, all right. So as you already know, I'll be talking about extra dimension solution to the hierarchy problem. And this is the overview of everything that I'll be covering. Let's move on to standard model. One of the most highlighted subject of science has always been the idea of unification, and the standard model, which is described by this gauge symmetry, and it is a gauge theory which consists of quarks, leptons, gauge bosons, and the Higgs boson. The dynamics of this theory is governed by a Lagrangian that depends on roughly about 20 parameters, and it is magnificent that with only these 20 parameters and within the formulation of quantum field theory, it is possible to compute a vast number of processes that involve these elementary particles. So this is the standard model. And despite the tremendous success that the theory of standard model, with its extremely high predictive power it has had, it is not complete and a few problems still exist. One may ask, for example, what dictates the parameters in the Lagrangian? And furthermore, fusing the theory of gravity with quantum theory yields a non-renormalizable quantum field theory. And moreover, after the discovery of neutrino oscillations, a couple of questions about the mass of neutrinos remain unanswered. And then there is the hierarchy problem, which is concerned with the delicate nature of gravity. So one could ask the question of why is the electroweak scale so much smaller than the four-dimensional Planck scale, which is the values are given over here. Or in other respects, why is gravity appears 10 raised to power 40 times weaker than the other forces. So what we do is consider a space-time of higher dimensions that is more than the usual 4 ones, and with the additional dimensions are so highly curved that they are undetectable at current energies. But the beauty of such an idea is that the single extra dimensional field can give rise to numerous 4-dimensional fields. So this extends the possibilities of unifying the gauge interactions with gravity. And this is known as the Kaluza-Klein mechanism, which I'll be talking in detail in a while. So the thought of extra dimensions arose from the attempts to unify the forces in nature. Kaluza and Klein recognized that Einstein's theory in 5 dimensions with one spatial dimension, if it is compactified on a circle S1, it can describe not only the 4-dimensional gravity, but electromagnetism as well. So as you can see over here, the idea is that the standard model fields are localized on a 3-brane, while gravity is allowed to propagate into the higher dimensions. So if we consider Newton's law of gravitation in 4 plus n dimensions, which is over here, for n compact extra dimensions, they have a size of which is L, and it is equal to 2 pi r. The constrained lines from the source mass are compelled to go in parallel in the additional dimensions, where when the distance within the regular 3 spatial dimensions is larger than the size of these extra dimensions, which is L. And so the law can be written as this form. If we compare this with the 4-dimensional usual form of Newton's law, we arrive at the expression for the size of the extra dimensions in terms of the number of those extra dimensions. So now let's talk about the difference in how standard model and gravity was developed. So the contrast between the two influences how we think about these two as well. So the standard model had developed hand in hand with quantum field theory, while general relativity was fully formulated about 100 years ago and was passed down to us as a geometrical theory. That is, that there is no such thing as gravitational force, but only the geodesic motion in curved space-time. So to make a quantum field theory out of general relativity requires all of the tools of quantum field theory that the standard model required. Now, I have already talked about GR, QFT in pre-defense, so I'll just quickly go through some of the things. We'll be staying in the harmonic gauge, which is specified by this condition, and the Green's function is in position representation is written as this. So to write down the Feynman rules, we take this action where it is the sum of the Einstein, Hilbert, and matter action. But we know that you cannot simply just add the two actions. We do some gauge fixing, and the gauge fixing part of the Lagrangian is this one. So finally, we arrive at this Lagrangian, whose equation of motion is pretty straightforward to compute using the Euler-Lagrange equations, and therefore which gives us the propagator for the graviton, where this P is defined over here, which is this last equation. This is 1/2, right? And the vertex Feynman rule, the vertex rules are given by, they correspond to the specific field. So if you have a scalar field, the energy momentum tensor for the scalar field is specified with this, and so you can write down the vertex rule using this T mu nu. Let's compute a process of two scalar particles that scatter via a single graviton exchange. So the amplitude is written like this by using the Feynman rules just derived or sketched above. And the interesting thing is, when you take the non-relativistic limit, in the non-relativistic limit, you can write down the amplitude in this way, and upon Fourier transforming this expression, you arrive at the Newtonian potential, which I think is enough to say that to verify everything that we have done so far. Now, let's talk about something called the teleparallel gravity. So what happens is that the Einstein theory of gravity, where the gravitational field requires the Christoffel symbols, is incapable of coupling to fermionic fields. Therefore, an alternate theory is needed, and that theory is the theory of teleparallel gravity, and it is a geometrical theory of gravitation in which the tetrad or the Verbian field is the dynamic variable, and it is constructed in terms of the torsion rather than the curvature. So let's talk a bit about tetrad fields. So it's a set of fields that are defined by 4 orthonormal linearly independent vector fields, which are given over here. And this is they transform like this under SO3, 1. And it sets up the local reference frame of an observer that moves along some trajectory. So you can also think of the components E0 as time-like, and the other ones are space-like vectors respectively. So over here, this the torsion-Levi-Civita connection is defined in this way, by using this relation, you can define another tensor, which is the contortion tensor, and this is what we will be using when we are going to couple to the fermionic fields. And the torsion tensor, which is this one, is defined as this. So getting to the field equations and the energy momentum tensor, we introduce a tensor like this. And then you just compose from the right hand side with the TABC, and you get this equation. And then upon doing some calculations which are given in the appendix below, you arrive at the Lagrangian density, which is this one, where Lm denotes the Lagrangian for the matter fields. Now, if we vary this Lagrangian with respect to the tetrad fields, we obtain this equation, which is given over here. And we can define the gravitational energy momentum tensor as such. So staying in the weak field approximation, we have this Lagrangian. We can write it in this way, from which we can again write down the graviton propagator in this form, now done in the view of the tetrad fields. For the vertex part, the Lagrangian for the Dirac field, it is given like this, and the interaction part of the Lagrangian reads this thing. Using this relation, we can write down this interaction Lagrangian in a compact form, which is this, and here this V, it is defined as the vertex interaction connecting 2 gravitons and 2 fermions. And but to sketch the interaction vertex that links 2 fermions and a single graviton, we use this approximation of our tetrad field, where this phi is the weak tetrad field and the delta is our Kronecker delta. And so you can write down the interaction Lagrangian as such, where this curly V, or the fancy V, is the vertex that connects single graviton and 2 fermions, and therefore this is the diagram for this vertex. Now, let's talk a bit about the Kaluza-Klein theory. It has always been a vital ingredient in attempts to form a relation between d is equal to 4 to higher dimensional physics. And the wave function of a scalar field, it can be expanded in Fourier series along the circle S1, as such. And here y is the coordinate that lives on the circle S1, and say it has a radius r, and n is the usual eigenvalue of the one-dimensional angular momentum operator. So for gravity, the linearized gravity Lagrangian is written in this form, and doing everything that we did above, following the same steps, we arrive at the propagator for the massive spin 2 Kaluza-Klein state, which is this one, and this quantity is defined in the appendix below. Okay, so the Lagrangian for an n-level KK state, which is coupled to fermionic fields, is written in this form. And again, from this we can write down we can sketch down the Feynman rules for the KK and the psi, where the psi is the matter field vertices. Now, using this, let me compute the 4 Fermion interaction via the Kaluza-Klein Graviton Exchange. And using the Feynman rules, we can write down this amplitude, the amplitude of such process as this, where C is it's some constant which is defined like this, and over here this d of s, it is again, I have represented this in the appendix below, and it accounts for the exchange of virtual Kaluza-Klein states. Now, Nima Akani Hamid proposed the reason that we don't experimentally see the finely spaced Kaluza-Klein excitations of the standard model particles. It is due to the fact that the entire standard model is confined to a 3+1 dimensional defect, which is called a 3-brane, which I have shown in my previous slides. And on the other side of the coin, gravity is not confined in such a way, and the Kaluza-Klein excitations of gravitons are then, of course, they're present. Now, the metric on 3-brane is given as this, and the brane action is found to be this thing, where this F is the tension, the brane tension. And if we use the interaction action and we expand the metric into its perturbation and impose some conditions on the perturbed field, the interactions between the standard model fields and the KK gravitons are specified via this action. So if you plug in the Kaluza-Klein expansion into the Einstein's equations, you arrive at these results. Now, you can interpret these results as that you can see, in fact, that only gravitons and radions couple to the standard model brane fields, while the rest do not couple to the matter fields on the brane, as you can see over here, that the right-hand side of these equations is equal to 0. So I'll end this with some concluding remarks, that with this, I have covered everything that I have promised in my synopsis. And a few future applications of this study could be such that the extra dimension solution is capable of making intelligible predictions to the question of why the universe is expanding at a rate beyond our wildest expectations. And this can be done so by computing the Kaluza-Klein KK decays. And so the cosmology at the early universe must be then examined with care and rigor with the existence of these KK states in the large extra dimensions. Furthermore, one can compute the decay of massive Kaluza-Klein states, as a massive KK state may decay to a pair of standard model particles, which may which includes obviously the spin 2 spin 0 KK states. So that's it. I end the presentation with.
Thank you, Dr. Sadi, you have any question?